Hello there, Mr. Sutton here, bringing you the AB Calculus 4-5 lesson on points of inflection. This will be a two-parter. In part one, we're going to figure out how to identify points of inflection for a function. And in part two, we're going to determine using concavity whether a critical point is a min or a max. This is going to be our second derivative test.
A point of inflection, which I'm going to call a POI for short, not an official abbreviation, but a lot of AP graders understand it. No guarantees, though. This is a point where the graph changes the direction of concavity, changing, for example, from concave up to concave down. And it's kind of subtle, but you notice there's this spot where you're concave up and then all of a sudden you're concave other direction. So we say that a point of inflection exists for f of x at x equals c if the following two conditions are met. First off, it has to be a point. In other words, f of c has to actually exist. And the other big condition is that f double prime has to change signs at x equals c. So this is our way of representing concavities with f double prime. Now, alternatively, you can meet this condition if f prime changes directions, changes from increasing to decreasing or decreasing to increasing, because this would also represent a change in sign for f double prime. Looking at it from the other direction, we have no point of inflection if f of c does not exist, or f double prime does not change signs, or f prime does not reverse directions. And in terms of justifying this, we typically have to keep track of but don't have to show the idea of f of c existing. What you do need to show is that the sign of f double prime changes or the direction of f prime reverses. So you have to show one of those two things to justify a point of inflection. Now that we've talked about what inflection points are and how to prove they exist, let's go ahead and find a few. Now the good news is the process is pretty straightforward. It's really just like solving for intervals of concavity with a couple extra steps. So we're going to start by just performing sign analysis on f double prime, just like we were finding where things were concave up and concave down. Pause the video and take a moment to do that with your sign chart and all of that. All right, so we need f prime first. That's 4x cubed minus 36x squared plus 96x minus 64. And then we're just doing sign analysis on f double prime, so we don't need to solve f prime or anything like that like we did earlier in the lesson. We're just going to do f double prime now. That's going to be 12x squared minus 72x plus 96. And now I need to set this equal to 0 and find critical values. Looks like I can factor a 12 out of this. That leaves me with x squared minus 6x plus, this will be 8. Two things that multiply to 8 and add up to negative 6. That would be x minus 2 and x minus 4. So we see that our critical values happen at x equals 2 and 4. All right, let's go to our f double prime number line here. So we've got critical values of 2 and 4. Testing out something in each interval. Be less than 2, let's use 0. That's going to give us a negative, negative, which is positive. Between 2 and 4, we've got 3. That comes out positive times negative is negative. And after 4, let's use 5. That's a positive, positive, boom, positive interval. All right, so at this point, we said we have an inflection point of f of c exists, and we're changing the sign of f prime somewhere. Well, let's just mentally check. Does f of c exist at 2 and 4? Well, yeah, this is a polynomial, so it exists everywhere. Okay, moving on then. We notice that f double prime is changing sign at x equals 2, because we're going positive to negative, and also x equals 4, negative to positive. Now, the direction of the sign change normally doesn't matter, so it's just any sign change we note. Based off of this, we can conclude that f has points of inflection at x equals 2 and 4. And again, a lot of AP graders recognize POI, but if when in doubt, write it out. All right, here's another problem, finding points of inflection still. Pause the video and see how far you can get on this one. Now, you got to be careful here. We want inflection points for f of x. They gave us f prime. So you actually only need a single derivative on this, which is going to be negative 2/9 x to the negative 4/3. And I'm just going to rewrite this in a radical form so the critical values are easier to find. So I can write this as negative 2 over 9, and downstairs I'm going to have the cube root of x to the fourth. Now I see here that since I don't have a variable in the numerator, this can never equal 0. So the only critical values I'll have are where x does not exist, or the f double prime of x does not exist. We see that that's going to be true if x equals 0. So I can say f double prime dne, which gives us a critical value, at x equals 0 for that denominator. But here's the other piece of this. Before you put 0 on a number line and start doing sign analysis, which you could, look at what's happening here. Down here, you're raising whatever the input is to an even power, which automatically makes it positive. Everything else in the denominator is keeping it positive. In the numerator, you've got a positive. The whole fraction is negative. This is always going to be negative as long as x does not equal exactly 0. Well, if it's always negative, there's no sign change. Since f double prime does not change signs, we can conclude there are no points of inflection for this graph.
For this next example, we're going to use the calculator. So given this function below, and notice this is f prime of x equals sine of e to the x, we want to know how many points of inflection f of x has on the interval from 0 to pi. Now, there's a couple ways we could think about this. We could figure out f double prime and use the graph to see where that changes sign, changes from positive to negative or vice versa. Another way to do it, though, since f double prime's sign is really the same thing as f prime's direction, we can also find where f has a point of inflection by seeing where f prime turns around, where it reverses directions. So pick one of those, pause the video, give it a shot, and let's bring it back together in a moment. All right, so let's see how that went. So I decided to go the route of seeing where f prime changes from increasing to decreasing or decreasing to increase, basically where we reverse directions or have a max or a min. So let me go to Desmos and graph this out. So let me get my function in here. I'm just going to call this g. So g of x equals sine of e to the x. And that's kind of a mess, so let me change my window a little bit to be from 0 to pi. And just to be on the safe side, I'm going to go from negative pi over 4 to positive 5 pi over 4, a little bit more than pi. And I'm going to make my steps, you'll notice here, go by pi over 4s. And then zoom in a little bit and count the number of direction changes. Looks like we've got 1, 2, 3, 4, 5, 6, 7, maybe 8. Is this a direction change that happens before pi, though? It's got to be inside the interval. Let me click on the function, and I get a dot for each of those direction changes. Clicking on this one down here, this is 3.159 and some change. So this is a little bit more than pi, which means it's outside our interval. So here was that picture again. And again, that's 7 different direction changes that are inside the interval. Since this reverses directions 7 times, we can say that f has 7 points of inflection on the interval from 0 to pi. So that is it for part 1 of this lesson. Feel free to pause the video and work on some of those homework problems, and join us next time when we talk about the second derivative test.
For our warm-up, take a look at the graph below of f of x. We want to know what is the relationship between concavity and whether a critical point is a min or a max. See if you can draw some conclusions just looking at this graph. All right, so we've got some critical points. For f prime, that's going to equal 0 at these turnarounds here. There's 4 of them. Now we notice that when we are concave up, when f double prime is positive, we have a min at x equals c. So when f prime of c is 0, when we're concave up, there's a relative min. And we notice that these other spots where we have concave down, like right here and right here, well, now we've got a relative max at x equals c, because you're at the top of a frown. So this is kind of nice. If you have 0 for the first derivative and you know the sign of the second derivative, you can use this to figure out whether there's a relative min or max. Now this does have limitations. This doesn't work so well if f prime of c doesn't exist, because if the first derivative doesn't exist, you can't even figure out what the second derivative is and whether it's positive or negative. In those situations, only doing sign analysis on f prime would help us out. But there are times when this is useful. For example, this example right here, Let g of x be a twice differentiable function, which tells us not a whole lot that's useful other than that you can take two derivatives. We've got g prime of 2 equals 0, g double prime of 2 equals negative 5. We want to know if g has a relative max min or neither at x equals 2. So this is a situation where you only have information about a function at a single x value. So we can't do sign analysis on g prime anymore. We don't know g prime of 1 or 3 or anything but 2. But in this situation, we know that g prime of 2 is 0. We know that g double prime of 2 is a negative number. So based on what we set up here, if the first derivative is 0 and the second derivative at that x value is negative, we're at the top of a frown, and we can quickly conclude that g has a relative max at x equals 2. So that's the gist of how the second derivative test works. Given that, see if you can use it to figure out whether we have any relative maxes or mins and what they are for this function. And I know you could use the first derivative test. Try out the second derivative test. All right, so we need one derivative anyway. First derivative is going to be 3x squared minus 12. And we do need to know where this thing equals 0. We need to know what the critical values are. So I am going to set this equal to 0 and solve. To do that, I can factor out a 3, leaving me with x squared minus 4. And I see that x squared minus 4 equals 0 if x is, let's see, add the 4 square root, so plus or minus 2. So these are two critical values now that we can plug into the second derivative to see whether that gives us a negative or a positive. Second derivative then, we need to know that now. That's going to be 6x, and then that minus 12 is just gone. So plugging in negative 2 to f double prime, that's 6 times negative 2, which is negative 12. That's a negative number. Since the first derivative is positive at negative 2 and f double prime is negative, that means we have a relative max at x equals 2. We're at the top of a frown if we're concave down. Now trying out f double prime of positive 2, that's going to give us positive 12, which is a positive. And in terms of proving anything on here, you have to show that your second derivative is negative or positive. You have to write out less than 0 or greater than 0. But if you've already shown that, and you've shown that f prime is 0 at these values, then you can go ahead and make your conclusion. In this case, since we're concave up, we're at the bottom of a cup, so that means f has a relative min at x equals 2.
And with that, we're all set with this one. Join us next time in part 3 of this lesson, where we use the third, fourth, and fifth derivative test. No, I'm just kidding. We're done.